This is 1.6 shapes of molecules and ions. So there are 4 points that you need to know in this topic. The first is to demonstrate understanding that the shape of a molecular ion is determined by repulsion between the electron pairs surrounding the central atom. The second is using valence shell electron pair repulsion theory to explain the shapes and the bond angles of molecules and ions with up to 6 outer pairs of electrons around the central atom to include these shapes. So we have linear, bent, trigonal planar, tetrahedral, pyramidal, octahedral, square planar, trigonal bipyramid and T-shaped. And then you have to explain the departure of bond angles in ammonia, in water, and those are from the predicted 109.5 degrees in terms of increasing repulsion between the bonding pair, lone pair, bonding pair, and lone pair electrons. And then demonstrate understanding of the difference between polar bonds and polar molecules, and be able to use the shape and dipoles present to predict whether or not a given molecule is polar. So, looking at the shapes of molecules, the shape of a molecule or ion is determined by the repulsion, and that's between the electron pairs surrounding the central atom. That can be between 2 lone pairs, between a lone pair and a bonding pair, or a bonding pair and a bonding pair. And the lone pair repulsion is greater than lone pair to bond pair repulsion, which is greater than the bond pair to bond pair repulsion. And this is known as the valence shell electron pair repulsion theory, or VSEPR. So as a result of these differences in size of repulsion, the greatest angles in the shape of a molecule will be between the lone pairs of electrons, and bond angles between bonded pairs are often reduced because they're pushed together by lone pair repulsion. So if you want to predict the shape of a molecule or ion, you take the following steps. The first one is to write down the number of electrons in the outer shell of the central atom. So this will be the same as the periodic table group number, except in the case of noble gases which form compounds, when it will be 8. You add 1 electron for each covalent bond being formed. For an ion, you adjust the number of electrons based on the charge. So for example, if the ion has a -1 charge, you add 1 electron. If it's a +1 charge, you deduct an electron. You now have the total number of electrons around the central atom, so you divide this number by 2 to find the total number of electron pairs. Then you take away the number of bonded atoms to find the number of lone pairs. And then you simply arrange the electron pairs in order to keep the repulsions between them to a minimum, taking account of the order of repulsion. So lone pair to lone pair is greater than lone pair to bonding pair, which is greater than bonding pair to bonding pair. So now if we have a look at some examples of molecules with only bonding pairs. So this table summarises the shapes adopted by molecules with between 2 and 6 bonding pairs of electrons around the central atom. So if we have 2 bonding pairs, our example is BeCl2, and the shape is linear. The bond angle is 180 degrees. So you can see here each chlorine is at 180 degrees to the central beryllium. The example for 3 is BCl3. It is trigonal planar, so if you look at that, it would be just like a little flat triangle, and the bond angle is 120 degrees between each of the bonds. So they're arranged in a flat triangle. The example for 4 is methane, CH4. It's tetrahedral, so if you imagine a little sort of pyramid like that with one of the hydrogens at each corner. The bond angle then is 109.5 degrees, and that's between each of the bonds around the carbon. For 5, it's PF5 is our example, and it's trigonal bipyramidal. So if you imagine a little pyramid like this with 3 faces, so you're imagining the shape blocked in around all of the atoms that are there. And there are 2 bond angles here around the It's like a trigonoplanar molecule with two fluorines, one above and one below. So in here, the bond angle is 120, and that's around those three fluorines, and then the bond angle is a right angle to the top and the bottom fluorine. And in SF6, it's octahedral. So again, we're imagining like a little pyramid, but this time with 4 points around the middle. And the bond angle here in all of them is 90 degrees. Next, we look at molecules with bonding pairs and lone pairs. So the presence of lone pairs increases the repulsion, and this results in bonds being forced closer together. So, for example, methane, which is CH4, ammonia, which is NH3, and water, which is H2O, all have 4 pairs of electrons around the central atoms. However, the 4 pairs have different combinations of bonding pairs and lone pairs. So those are the examples we're going to look at. So methane, as we saw above, 4 bonding pairs. There are no lone pairs in it, and it's tetrahedral with a bond angle of 109.5, as we saw. With ammonia, there are 3 bonding pairs and 1 lone pair, which makes it pyramidal. Now the bond angle then is 107 because this lone pair here repels the bonding pairs. So you see that the bond angle is 2.5 degrees smaller in the ammonia than it is in the methane. Then if we look at water, we have 2 bonding pairs and 2 lone pairs. So the shape this time is bent. So if we imagine the 2 lone pairs here, they have a much greater repulsive effect on the bonding pairs and reduce the angle here to 104.5. And if we look again, it's minus 2.5 degrees from the ammonia. So when we go from methane to ammonia to water, we're reducing the bond angle by 2.5 degrees each time. Now, as the number of lone pairs on the central atom increases, the smaller the bond angle due to the increased repulsion between the bonding pairs and the lone pairs. So the explanation of the shape for water: the electron pairs repel each other. There are 2 bonding pairs and 2 lone pairs of electrons. The lone pairs have greater repulsion, and the molecule takes a bent shape to minimize the repulsions. So, some other examples here. If we look at XeF4, there are 4 bonding pairs, 2 lone pairs, and it's square planar. So we have a lone pair here and a lone pair here, and the bond angle then between each of those is a right angle. In ClF3, there are 3 bonding pairs and 2 lone pairs, and it's what we call T-shaped. So the angle here is 86 degrees. So if we imagine these 2 lone pairs here, they're distorting the shape of the molecule, making it T-shaped. And then finally, XeF2 with 2 bonding pairs and 3 lone pairs this time. This makes it linear, so imagine the 3 lone pairs here, and we have just 180 degrees as the bond angle. Now there's some examples involving coordinate bonds. And a coordinate bond forms by converting a lone pair of electrons into a bonding pair of electrons. So for example, ammonium ion, NH4+, has a tetrahedral shape with a bond angle of 109 degrees. So the electron pairs repel each other, and the 4 bonding pairs repel equally. And the molecule takes up the shape to minimize repulsions. So remember that ammonia, NH3, is pyramidal because there are only 3 bonding pairs of electrons and then the 1 lone pair, but an ammonium ion is tetrahedral because it has 4 bonding pairs. So looking at molecules with double or triple bonds. So a double or triple bond counts as 1 bonding pair of electrons when you're determining shape. So carbon dioxide, CO2, has a linear shape with a bond angle 180 degrees. The electron pairs repel each other, two sets of bonding pairs repel each other equally, so the molecule takes a linear shape to minimise the repulsions. Now, if we think about polar bonds and polar molecules, a polar bond is a covalent bond where there is unequal sharing of the bonding electrons, and this occurs if there's an appreciable difference in electronegativity when the bonding atoms, or between the bonding atoms, and if there are partial charges, your delta plus and delta minus, they appear on the bonding atoms and you get a dipole. So if a molecule contains equally polar bonds arranged symmetrically, then the polarities of the bonds cancel each other out and the molecule is non-polar. So for example, carbon dioxide is a linear molecule with polar bonds, but overall it is non-polar. So if we think about that, we've got our carbon with two oxygens. Each oxygen is going to be slightly negative. So we have two dipoles here, but they actually end up cancelling each other out. So there's no overall dipole and the molecule is non-polar. So if we take another example of carbon tetrachloride, CCl4, each of those bonds would be polar, with the chlorine being delta minus. But as the overall shape of the molecule is symmetrical, the molecule itself is not considered polar. So water, on the other hand, has an unsymmetrical bent shape and it has polar OH bonds, so it is considered polar. So if we take a little example here of the water, we've got delta plus for the hydrogens, delta minus for the oxygens. So overall, there is a resultant dipole there. So the polarity of molecules can be investigated by bringing a charged rod, either positive or negative, to a jet of flowing liquid. The polar molecules will respond to the charged rod. Non-polar molecules will not deflect. And I'm sure you've tried this at home with a ruler, a plastic ruler, and a very thin stream of water falling from the tap. If you charge up the ruler, you can deflect the water, and you can do that also here using a burette. And you charge up your static rod, hold it close to the stream of liquid. If it is repelled or attracted, you know that it is polar. If it just flows straight down instead, you know that it's not.